if you don't mind, I start and then we wait for a result. Well, dear friends, ladies and gentlemen, we are today very honored to have Professor Sir Tenjinder Virdee. We call him Jim Virdee, FRS Fellow of Royal Society, who is our guest today and will tell us about the voyage to the origin. I mean, you will see what it means in few seconds. Tenjinder Virdee is Professor of Physics at Imperial College, London. Over the last 30 years, he has concentrated on physics and experimentation at CERN, at, especially Large Hadron Collider. He is one of the two founding fathers of the compact muon solenoid, the so-called CMS at LHC, the experiment that Iran is also involved in now, thanks to him and his colleagues who have provided such opportunity for us, and has played a major role in all phases of the experiment, from the conception at the beginning through the construction and extraction of science and proposing new experiments to it, new detectors and so on. He was involved in almost all the key scientific and technical choices made for the experiment. He pioneered some of the techniques used in the discovery of the Higgs boson, announced by CMS in 2012, in July 2012, that we also witnessed it directly in Iran in several places. And this, at the same time, Atlas was also involved, and they announced it jointly. This was a great discovery for the century. It gave us a good beginning for this century of physics. Tijinder, or Jim, was spokesperson or the leader of the CMS collaboration from 2007 for a long period, and where we started to get the data. I was involved then and witnessed all this in person. He was deputy spokesperson also in the earlier times from 1993 to 2006 for a long time, for about 13 years. Current work of Tijinder involves studies of the newly found Higgs boson. He's most interested in Higgs boson, search for physics beyond the standard model of particle physics, and the design of the upgrade of CMS detector for high luminosity. Soon we will, it's going on now, and soon we will see that LHC and CMS will start working with much better condition and give us new results, hopefully. He has won several prizes, among which I can name UK at 2009 UK Institute of Physics Chadwick Medal, and in 2013 the European Physical Society HEP Prize. In 2013 he got Fundamental Prize for Physics, the Fundamental Physics Prize. At 2015 IOP Glazebrook Medal and Prize. In 2017 American Physical Society Panofsky Prize, and 2020 Blaise Pascal Medal of European Academy of Sciences, and many other awards that we cannot mention at this short time that we have got. Jim was elected as Fellow of the Royal Society in 2012 and was made Knight Bachelor, that's why we call him Sir, in 2014 Queen Elizabeth's birthday honor list. Jim is passionate about promoting the benefit of science and the importance of society. Apart from its value for science, he also interested in the application of it into society and making our life better. He funds diverse and impactful educational and scientific activities in schools and universities in Africa, India, and UK, and projects also in sub-Saharan Africa countries through Verdi grants in collaboration with the UK Institute of Physics. Well, today we are honored to have Jim Virdee to tell us about the journey to the origin. And I invite you, Jim, to start your talk.
Yes, thank you very much, Sam, for this nice introduction. And what I'll do is I'll switch my video off during the talk because it may be bandwidth problems. And I'll switch my video on for the question and answer session. And again, thank you very much for this kind introduction. Talk today is about looking at the origin of our universe and being able to figure out what happened in the early moments of our universe. A lot of it depends on particle physics, as I'll show in a few minutes. Now, I'm going to talk quite a bit about the Large Hadron Collider in Geneva, where we can probe our universe moments after the Big Bang, fractions of a nanosecond, in a sense, after the Big Bang. And the idea is to tackle some questions about the origin of our universe, its evolution, and its composition. And these questions are quite fundamental, include what is the origin of mass, and I'll say more about that. What constitutes dark matter and dark energy? We still don't really know what those are. And how many dimensions of space and time do we live in? And why is the universe composed of matter and not antimatter? And clearly, the answers to these questions have the potential of altering our perception of how nature operates at the fundamental level. Now, the discovery of the Higgs Boson at the Large Hadron Collider in July 2012 is one of the most important scientific discoveries of this new century. And it completes the particle content of the Standard Model, which I'll say more about. It's a theory which describes how visible, and I use the word visible advisedly, in exquisite detail. So I will actually...
Excuse me, Jim, did you move your presentation? I mean, we don't see your PowerPoint changing. You're fixed on one page. If I'm not...
I haven't actually
did you move on?
No, not yet.
Oh, you haven't changed it. Sorry. I'm sorry.
Okay. No. So I'll say something about the Big Bang towards the end of the talk. And I'll also discuss the fundamental particles and their interactions, and say a few words about the long journey to the discovery of the Higgs boson, especially in the construction of the CMS experiment and some of the engineering challenges that we face, the technological ones. And towards the end, I will touch upon the fact that our current understanding of matter and forces is incomplete, and that's why we're looking for fundamental physics beyond the Standard Model. And if we find it, it should illuminate the road ahead to the cherished goal that Einstein had laid down of a unified theory of all physical phenomena in nature. And I will say a few words about the societal impact of the fundamental scientific research that we do at CERN and the LHC as such. So let me go to the next. We're all very aware of the fact that there's a wonderful variety of phenomena in nature, and one of the primary goals of physics is to understand this wonderful variety in a unified way. Now, the question really arises, can we describe these in terms of underlying principles of great simplicity and beauty? And if we can, what benefit do we get as humankind? And I think I wanted to stress that point. Of course, the answer is that we can to a great extent. And also the greatest advances that we have made in the past have been steps towards this goal of trying to understand things in a unified way. One only has to look at the unification of terrestrial and celestial mechanics by Isaac Newton. So this is shown here. And the theories of optics and electricity and magnetism were combined into electromagnetism by James Clerk Maxwell. And I'll say a few words about that. And then there is the issue of the space-time geometry, which was combined with the theory of gravitation by Einstein in the early part of the 20th century. And these two graphs actually, this graph actually shows that, depicts, and I'll say, make a comment about this. So there's also the chemistry and atomic physics through the advent of quantum mechanics, which has really altered the way we actually think about nature. So you can see that here I'm showing this GPS system, which requires you to actually understand both the special theory of relativity and the general theory of relativity of Einstein. If you don't actually take account of those theories, you can be off by hundreds of meters within a few minutes if you're driving in a car, for example. So these have some impact, although they're very esoteric theories. And clearly, electricity and magnetism have been combined into electromagnetism. And as I mentioned, with the advent of quantum mechanics, we have electronics. And the electronics stem from our understanding. All of electronics, how it works, stems from our understanding of atomic physics, quantum mechanics, and electromagnetism. And on the right-hand side, you have the recent meaning last 50 years, unification of electromagnetism, the weak interaction, which actually describes to describe the phenomena on this row here with the same equations. They are obviously very diverse phenomena. So this is the power of unification, that you can take different phenomena and understand them in a very fundamental way, which leads to great technological steps, which allow us to make instruments and so on. So particle physics is essentially a modern name for a centuries-old effort to understand the laws of nature, which I've just mentioned in a few minutes. And that's a phrase from Ed Witten, who I think spoke to you. Now, in particle physics, we aim to answer two following questions. So what are the fundamental or elementary constituents that make up our universe? And what are the forces that control their behavior at the most basic level? And what it means experimentally is that we make particles interact and study the products and properties of the result of the interaction. So that's a very simple thing. And we devise detectors that allow us to measure the energy, the direction of the products as accurately as possible. And then we use computers to reconstruct what happened during the collision as such. Now, this is one of the first collisions that took place. You can see the 2009 December 14th timestamp, and protons are coming in the directions, one from there and the other one from there, and interacts. And you can see already some characteristic signatures, bunches of particles which represent quarks, in fact, fragmenting. And so you can see even in this simple picture, one of the first ones we took at LHC is quite rich in detail. And that's when I mentioned that we try to measure the energy and the direction, identity of all the particles. There are three layers there. You can see three types of objects singing. The fourth layer is not shown here. So that actually tells you how we actually going to do the work that we set out to do. So within a few months of to take data, we could produce plots like this. Now, this is a plot where on the horizontal axis, we've taken from every event that has two muons, we take the energy and the direction of the muons and combine it to what we call an effective mass, the mass from which this object would have, these two muons would have emerged. And you just plot it in terms of the mass and how many times you see it. And you can see most of the time there's no correlation, and then it looks like noise. So this is noise in a sense, random coincidences. But sometimes you see peaks, and these peaks are actually what the particles are. So these are bound states of quarks. In fact, these are the normal UND quarks here, CC bar and the BB bar bound states. So within a month, we could actually track back the history of particle physics. These were discovered in the 1960s, and this one is 1983. So you can see something like 50 years of particle physics in this plot here. One other thing we used to do is to actually, the reason for making this plot was to understand whether our detector within the first few months was actually working as we wanted it to work. So there's a certain width of this resonance which has been blown up here. And that width should have been about 70 MeV. That was the design goal, and we measured it to be 67. So this was one of the plots that told us that our detector was actually working very well, which is astonishing in the sense that they're very complicated experiments, and within a few months we were getting plots of this nature. So that's very, very encouraging for us. Now let me discuss a little bit about matter and forces, and I develop that story a little bit more. Now, I think most people are familiar that matter is made of molecules. Molecules are made of atoms, and atoms have electrons and nuclei around which they orbit, and the number of electrons determines the chemistry of materials. If you look at the nucleus, you have a neutron and a proton in there, and the neutrons, and they're held together. So, for example, the atoms are bound by the electromagnetic force, and these are bound by the strong nuclear force. Nuclear force, and the quarks inside the protons and neutrons are bound by the strong nuclear force. Now, to just orient you respect to the energies we're going to be talking about. So, if you wanted to remove an electron from let's say hydrogen atom, you need to expend some like 13, 14 electron volts. So that's about 10 times these 1.5 volt batteries worth of energy. And to remove a proton or a neutron, you need some like 10 MeV, 10 million such batteries. At the LHC, we have about 6.5 TeV per beam, so that's 5 trillion batteries, just to give you an idea what TeV means. So you can actually equate it in terms of the batteries as such. So that's the, and I developed that a little bit more. And then you have the 4 fundamental forces, the strong, which is binding the quarks inside the proton and the neutron. The electromagnetic you're very familiar with, and gravitational, of course, you're very familiar with, and the weak interaction, which is the interaction responsible for beta decay, for example, and burning of the sun. Now, in particle physics, we only deal with these 3 forces because the gravitational effects are very, very weak, and we never really observe them. And so we have theories of these 3 interactions, and all the known forces in the world that we can perceive can be attributed to one of these 4 interactions. Now, over the last 100 years, the combination of quantum mechanics and special theory of relativity, along with lots and lots of particles that were discovered in the 50s and the 60s, led to the development of the standard model. It's a sort of a theory of particle physics. We call it the standard model. And the question really is that the final periodic table of fundamental elements, or is there structure to further structure? We don't really know the answer to that. But on the left-hand side, you see the matter particles. So there are matter particles seem to be organized in 3 families. The first family is the one that we are familiar with, everyday matter, for example. And the second 2 copies, the further copies, we don't know why they exist, but they can be made in the laboratory, and they don't normally exist in everyday life because they decay into these types of particles, the first generation. On the right-hand side are forces, because if you want to exert a force, you need to exchange something. You need to exchange packets of energy. And so these are the quanta that actually are exchanged when 2 entities interact. And the quanta the energy is carried by the force. And the Z and W are the quanta of the weak interaction. The photon is the quantum of the electromagnetic interaction. And the gluon G is the quantum of the strong nuclear interaction, which holds the quarks and together inside the neutron or a proton, for example. Now, clearly, we have particles that interact, so you must have a theory that is interacting theory. On the right-hand side, it's a simplification of the quantum field theories of the 3 of the 4 fundamental interactions that I've just mentioned. It is a very, very successful description of our visible universe at the short distances. So the first line contains the fields, the force fields. The second line contains the matter fields, describes the matter fields rather. And then we have the interaction terms. So how do these things interact with each other? And that's in the third line. And the fourth line describes what happens with the Higgs boson. And the Higgs boson actually plays a very fundamental role. It's a sort of a keystone which holds all of the standard model together. And it gives masses to the particles like the Z and W, and leaves the photon massless when the electroweak unification takes place. So you have a force being unified where some of the mediators are very massive and one of them is massless. And how does this really happen? And that's at heart what the Higgs mechanism, Higgs-Prout-Englert mechanism actually is about. And so that plays a very fundamental role in our understanding of how to set up this theory as such. So no wonder we spend a lot of time looking for that particle. If it hadn't existed, there would have to be something else that fulfills this role, because we know that there are these forces are rather similar, can be unified, but actually understand how the photon could remain massless and these guys get a mass of order of 100 times the mass of the proton, for example. So the science of the LHC when we started was can be summarized in this slide in a general way. So the first one was Newton's unfinished business, in a sense. What is the origin of mass? Remember, he developed the equation force equals mass times acceleration, and but he didn't tell us what mass is actually. So what is the origin of this thing? And in a sense, this goes to the heart of our existence, because mass is what gives our universe substance. So if an electron didn't have a mass, then we wouldn't be able to form atoms, and we wouldn't be here discussing this thing. And of course, there are some other problems related to this embarrassment, that we don't actually know 96% of what the universe is made of. That's why I'm cautious in saying that the Standard Model describes the visible, and it doesn't describe dark matter or dark energy, which is 96% of the universe. So what I'm talking about is about 4%. And of course, there's nature's favoritism. Why is there no antimatter left in the universe? And so we're still trying to understand that question. We have some clues as to what is going on, but we don't have a deep understanding of exactly the size of it. And there are other secrets of the Big Bang. What was the matter like during the first second of universe life, and how many space-time dimensions do we live in? Is it just the 4? Is it 10? And some of these go to the heart of our existence. Even dark matter, in a sense, is needed to form galaxies, as I will say right at the end. And without the formation of galaxies, we wouldn't exist. So dark matter was needed in a billion years after the Big Bang to seed the formation of galaxies as such. So these are really fundamental questions. Now, I just want to give you an idea what it means to be accelerating particles. So clearly we need particle accelerators, and we accelerate particles to very high energies, as I've just mentioned. But the high energies allow us to do three things. They allow us to study the young universe, because Boltzmann's relation, which is E equals KT, means if you have very high energy, you're looking at very high equivalent temperatures. It's not a thermometer you can put there, but its equivalent temperature is very high. And we know that the early universe was very hot. And so that means that if we actually have very high energies, we're going back in time. So we're revisiting the earlier moments of our ancestral universe. So in a sense, this makes the LHC a very powerful telescope. Now, of course, to discover new particles, we need to make them. And through Einstein's relation, we need a high energy to make a high mass. That's fairly familiar. But you can also look deeper into nature. So you can look at, for example, the quarks and see if they have any structure. And that is done by having the equation that was set forth by de Broglie at the beginning of last century, that energy is inversely proportional to the size of the object you're trying to observe. So that's the radiation that you need to actually discern that whether there is structure or not. So we've actually now know that within one few hundred thousandth of the size of the proton, there is no structure to the quarks as such. So this we continue, but it doesn't look like quarks look to us at the scale that we are probing as point-like objects. So all of this allows us to observe phenomena and particles normally no longer observable in an everyday universe, and all of this in a controlled way in a laboratory. So that's the mission that we have. Now, studies in particle physics require, obviously, the accelerators, which I've just gone through. It requires detectors, so these gigantic instruments that record the resulting particles as they stream out from the point of a collision. And you need massive computing to collect, store, distribute, and analyze the vast amount of data produced by these detectors. So you can have the structure that we set up allows people, for example, even in Iran, to actually access the data, all of the data that we take in CMS experiment, and they can analyze whatever they wish and find whatever their prejudices are and their inclinations are. So this is a collaborative science on a worldwide scale is needed, because to make these detectors requires the talents and the resources of thousands of scientists, engineers, technicians, and support staff. So that shouldn't be forgotten, and that's one of the reasons why at the beginning of the 1990s we went around the world to try to attract people to join us, and sometimes help them organize themselves and also to learn how to do experimental particle physics. So that was a very, I think, satisfying experience, certainly for people like me, to see all of this mushroom and develop. And now I'm talking to you remotely as such. Now, the accelerator, so the protons are accelerated by very powerful electric fields. And in a way, it's very similar to what a surfer does when he surfs a wave, as I've shown downstairs. Instead of the water wave, it's an electromagnetic wave. And they're guided around by, in the circular orbits, by superconducting dipole magnets, which you can see. You can just about see the curvature at the end of this tunnel there. So there's a small curvature, it's 27-kilometer diameter, circumference tunnel. Now, the dipole magnets operate at 8.3 Tesla, and they have to be cooled to superfluid helium. And the superfluid helium is a very interesting engineering material. I may say a few words if somebody asks me a question about it. And the protons travel in a vacuum tube inside here in opposite directions. So the temperature is lower than the temperature of interplanetary space, and the vacuum is better than that. So these are extreme engineering requirements, and of course they've been successful. Now, in terms of the detector itself, what does the detector do and look like? So we can draw an analogy. When you design a detector to start off with, you actually have physics that you want to do in mind. And so you design it for that purpose, in a sense. So in the case of CMS, clearly the search of the Higgs boson was a driving feature. We can draw an analogy with a cylindrical onion, and there are 4 principal layers as they're shown. And each layer contains technologically advanced detectors, and each perform a specific task. And together, these layers then allow us to accomplish the mission statement, which is to identify and precisely measure the energies and directions of all the particles produced in the collisions. What I'll show you in CMS is a transverse cut of this onion-like structure, and you can see the detail of how this cylindrical onion gets transformed into a detector, which is the next slide. So this here you can see now. So that's a slice of the cylindrical onion. That's the first layer. That's the second layer there, which is, so the first layer is made of silicon trackers, which allow us to measure the trajectory of charged particles. The second layer is lead tungsten crystals in the CMS. It allows us to measure the energies of the electrons and the photons. And the photons is quite important because that's a signature of the Higgs boson. I'll come to that later. And the third layer is the hadron calorimeter, and Iranians were involved in this one. I'll show a few slides on that. And the fourth layer is the muon system. So this allows us to measure all of these, long-lived standard model particles very well. One of the other things that I should mention, these are also PhD factories. So there are about 1,000 students, PhD students, working on their thesis at any one moment in CMS. So really is a big, big scientific experiment. Now, I just wanted to give you an idea that these things were not easy to actually build and operate and get them to do the work and perform as we wished them to perform. So I just pick on the second layer, which is the lead tungsten crystals. And the physics driving the design was to measure the energies of the photons from a decay of the Higgs boson to a precision of less than 0.5%. And for that, the best way of doing that is to look for some homogeneous material like a dense scintillating crystal. So we were shown some of lead tungsten crystals in 1993 with yellowish samples, and there was no way that those could actually work in the experiment. Yet they were tantalizing us in the sense that they were very dense and you didn't have to grow them very long, which was a great advantage. They didn't produce much light, but maybe one could overcome that by some other means. But nevertheless, if we wanted to make use of those crystals, we had to do a lot of R&D. So we had to improve the radiation hardness because a billion pairs of protons interacting every second inside the heart of the experiment lead to ferocious radiation conditions for detectors. I won't really say very much about them, but that was one of the biggest challenges we faced, actually, to make sure that the detectors can survive 10 years of such numbers of interactions. We needed to make sure that the purity of the substances was lead oxide and tungsten was good, and the stoichiometry, the fractions in which the lead oxide and tungsten oxide are mixed. And there are obviously defects because these are crystals, and you have to compensate for the defects by introducing impurities of just like you do in silicon, for example. And you had to do a lot of prototyping work to make sure that the performance that we were looking for, which is shown in the box above, can be reached. And then you had the problem of the mass manufactured. We started with centimeter cube samples, but we needed something like 10 cubic meters of this substance, and that was mostly done in Russia. And so we had a factory that was running around the clock for about 10 years, producing these crystals. And then clearly, once you produce these things, you have to integrate the systems, whether there's tooling required in assembly, the cooling systems, electrical systems, and so on and so on. And the installation and commissioning, and then collision data taking started in 2009, and we found the Higgs boson. And the strongest signal that we found in CMS was, in fact, in the two-photon mode, and I'll show you that. So this all in all took about 20 years of work. This gives you some idea of the complexity of the things and the phases in which you had to go through to build the detector that we use today. Now, just to give you an idea, so I'll start from here. So this is how a crystal boule is grown. So it's grown in an oven at the level of about 1200 degrees. And there's a crucible in which the melt is, and the crucible is lined with platinum. And this platinum, there was about $20 million worth of platinum in this factory, which was signed off from the Russian Federal Reserve by Putin himself. He put the signature there, and there was armed guard in the factory to just make sure the platinum did not disappear. It's used as a catalyst, so you don't actually lose much of the platinum. Maybe 4% is lost in the production process. Now, then the boule is cut into shape, and polished, and there are 10 crystals put into a structure, which is a holding structure, which is self-supporting, made out of carbon fiber. And then we have structures which take 400 crystals, and then we have what we call supermodules of 1700 crystals. Now here you see an empty space, and the next slide you will see that that empty space has actually been completely bring it back in. So that is where the electronics sit and the cooling system sit, and these things have to work for once they're in there, all the connections must be perfect, because to open the detector if something goes wrong, it takes 1 year. So fortunately, we've been running for about 10 years, and we've only lost order of 1% of the channels. So that's a very high fidelity work, quality control and quality assurance of the highest level, almost the space level, because you can't really touch these things. And then you get into the 36 supermodules, and the detector is ready, and that was in July 2007. And so the something else which we had to do was to start with, again, I'll have to do because I can't show you the slides. So let me try that because I have to actually. So for the hadron calorimeter, we decided that we use cartridge brass. And for cartridge brass, the Russians were supposed to contribute. And one of the technicians who had worked at the Russian Navy actually realized that there were a lot of shells which were being decommissioned from the Russian Northern Fleet in Murmansk. So the casings of the decommissioned shells were, 1 million of them were melted down and turned into plates, which is this thing. And then ended up machined and as plates that were put into the experiment itself. And so you can see swords to plowshares kind of stuff. Now, there were also very heavy engineering activities, very complicated. And this is the lowering of the detector. The detector was assembled on the surface, and it was lowered into the underground cavern And this is a 2,000-ton piece. What you will see when I run the time-lapse picture is that this thing is lifted a few centimeters by a crane, which is on the outside of the building, just a few centimeters above this cover plate, which is 1.5 meters thick reinforced concrete, which can take about 3,000 tons. So this is 2,000 tons. And let me start that movie now and see if it, so you can see the cover plate retracting, and this thing is slowly going down on 4 multi-strand cables, which you see there, and there. It started at 6 o'clock in the morning, and you can see the daylight piercing, and these are the feet of the gantry crane on the outside of the building. And soon you will find, it took about 10 hours operation, and here is now kind of getting into the cabin, which is about 100 meters underground. And there's very little clearance on each side, so it's a hand's width of clearance. So they had to come down very, very straight. And if any distortion had taken place, we wouldn't have had an experiment as such. So you can see some spectacular operations taking place. Now you can see this thing is quite bald, and so the next slide is 7 months later. This thing looked like this. There's enormous numbers of cables, cooling pipes, optical cables for signal transfer, low voltage coming in, and so on, and high voltage coming in. And also the cables were generating a fair amount of heat. They needed to be also cooled. None of these things can be easily accessible. It takes about 6 months to access this area here. And so again, high fidelity was of great importance. Now, let me just say a few words about the Iranian contribution. So there are 2 institutes from Tehran and Isfahan. And the contributions to the CMS construction was in the forward hadron calorimeter. So you can see this lowering operation I just showed you. The first lowering operation was of this device itself. And this is a picture taken, I think, in HEPCO near Tehran, the company there. And so you can see the structures, the support structure and the outer structure, which was manufactured in HEPCO. Now the Iranian physicists are working on the operations, and also a lot of the young ones are doing physics analysis and looking for new physics, in fact. So that it's very, very good training ground actually for learning how to do research. Now we are also now going to upgrade our detector to be able to take 10 times more integrated luminosity than was foreseen. So that requires us to change a few things. And the Iranian contribution is taking place in what's called the new link system for the muons RPC system. The idea is to make these link and control boards and improve the timing resolution from 25 nanoseconds to 1.6 nanoseconds, and also have a lot more data coming out. And all of this thing, there are about 1,300 link boards and about 200 control boards. So this is electronics which sits in the underground control room. And so good progress has been made. The design, the construction, the quality control, and the validation is all being carried out in itself. So this is really something that is happening in Iran, and what will be sent is a working system. And of course, the Iranian scientists and engineers will come and install it and make it work. So we need this stuff to be ready by about 2027, installed. So there have 3 link boards been produced, validated, and the firmware is being developed, and the project is on good track. So this is again something very, very, I think, important to learn how to do research, both from the engineering point of view, from the students' point of view, and also from the software point of view as such. Now, the work was quite well appreciated. So this is the 4 people from CERN came over to just check, and they're doing a load test of all of them standing there. And the work was of high quality, and CMS gave the gold award to the HEPCO, and I think this is a HEPCO leader receiving the award from our first spokesperson, Michel Della Negra. Both of us actually have been to Iran and give talks there to encourage people to join us. So now this is now what the detector looked like in 2008, and the HEPCO stuff uranium contribution is, you can just see by the yellow, the orange is there. It's encased, and you can give the size is given by the person standing there. So the experiment was ready, closed in 2008 to take data. Before I go into the science itself, I just wanted to pick up the issues of the work that has a societal benefit as such. And I'll take just two examples. I can take many, many examples. But let me start with the World Wide Web. So this is a document, it's a two-page document which was signed by the CERN Directors of Research in 1993 that actually gave the rights to the World Wide Web to anybody who wanted them. So I just pick up the highlight of that previous document. So CERN relinquishes all intellectual property rights to this code, both source and binary form, and permission is granted for anyone to use, duplicate, modify, and redistribute it. And this is April 1993, just less than 30 years ago. So that is a document which actually ignited the World Wide Web, and we can't really operate without that any longer. So that has obviously had a huge societal impact and hopefully benefit, although we're still learning how to alleviate any abuses that take place. Now, the other thing I wanted to actually mention is that, I mentioned fundamental physics, and, you can't go more fundamental than Dirac's equation, which I don't expect you to understand, but I just wanted to tell you from that equation, which was in the early 1930s, it was just trying to actually make sense of how the electrons move. And from that, it's his description, Dirac's description of electrons consistent with Einstein's special theory of relativity and quantum mechanics. So it predicted two things. It predicted the existence of antiparticles in the positron, which is the basis of positron emission tomography, and it explained spin, and that's the basis of magnetic resonance imaging. So you can see from that equation, you actually have the technologies much, much later, obviously. And for that to happen, you had to make sure that there were certain other things that happened, like the operation of the first cyclotron. And that's where the anti-electron was discovered. But you also need cyclotrons to produce radionuclides, which give you the positrons, for example, for the PET cameras. So you bring 18-FDG, fluorodeoxyglucose is labeled by fluorine 18. And then you use PET cameras to detect the two photons from the annihilation of the positron with the neighboring electron, and you localize it. And for that, you use APDs, heavy scintillating crystals that I was just talking about, and the photo devices which can operate in magnetic fields and so on, which now are being combined with MRI scanners. So you get both the MRI image and the PET image at the same time. And in fact, one can argue that the scientific basis of much of medical imaging is steeped in nuclear and particle physics. Now, of course, life is not that simple when you look at developments. And so here is the development of positron emission tomography. I won't be able to go through all the slide, but there are three parts to it. There's science, there's society, and industry, and they all have to work together. The science is that predicts it, and Anderson discovers the positron. Lawrence makes the first cyclotron. And you have things like the first photomultipliers, which allow you to detect light. And also Brookhaven National Laboratory, the first synthesized FDG, which is used as a labeling material. And we have advanced scintillators, for example, BGO and LSO, and solid-state photomultipliers. So these are the works at LEP and LHC, the CMS as such. And from the societal point of view, it is obviously things take off when medical insurance companies can actually allow you to reclaim the expenses. And so this is actually showing the medical reimbursement, which is possible by Medicare. And also the industry now needs to make these instruments that are cost effective. And the next slide, you can see that you can get a lot of information and a lot of help in, for example, detecting early Alzheimer's by using such scans. I wanted to pick on the costs issue. So these are the costs of 2016. So the work we actually do is because we actually want very large numbers of, for example, the detection channels, and also the infrastructure that we set up shouldn't cost very much. All in all, the work we do is to bring the cost down of, for example, in this case would be a PET scan. So in 2016, it was something like $1,500. If I had a PET scan today, it's about $150 or something like that. So part of the work we do in developing our detectors do fundamental science actually percolates into lower costs of the standard things we sometimes take for granted, which are very costly 10 years ago, 15 years ago. And of course, we also come up with newer devices. So for example, now we're using heavy scintillating crystals coupled with the silicon photomultipliers to get a timing resolution at the level of 30, 40 picoseconds. Now that will also be put into the PET scans. In fact, it originated from somebody working on the CMS crystals who set up a project which tried to measure the photon at a precision of tens of picoseconds. This allows you to put a lower dose into the patient because you get a coincidence which is much cleaner. Both the coincidence occurs both in space and in time, so an extra dimension is added. So now let me go to the science itself. And so when I showed you the detector was closed and ready. So the first thing you have to do is when you start using an experiment is to see if the experiment performs as you wished it to, as in other words. And the other thing is that there is a whole body of physics that is known. So if your detector is working correctly, it must reproduce the known physics correctly as well. If it doesn't, then there's something wrong. And it's only then can you look for new physics as such. So I've shown you the detectors did perform quite well. I showed you one plot. There were hundreds of such plots which told us the detectors were performing very well, and we were very pleased with that. And then within a few months, we were able to produce results measuring things which are known in standard model physics from previous experiments. Now, this is the set of measurements which are up to date, June 2021. So these are the W and Z productions, dye boson production, WWWZ, then tri-boson production, so the cross sections or the probability of them being produced for a given proton-proton interaction is decreasing. You can see something like 8 orders of magnitude here. And so we were reproducing standard model physics very soon after starting data taking. We knew that the detector was physics ready in a sense as well. And this plot actually shows you that there's very little discrepancy. There is no discrepancy between the standard model predictions and what we are measuring. So that is a bit of an issue in the sense that we would hope that we would be able to find new things, but the standard model, which describes, as I said, the visible universe in exquisite detail, and that exquisite detail you see in this plot here. And so what we're looking for is something which deviates from a line. A line here is what the standard model prediction is, and the point is what the data is. In some cases, you can't even see the line because the data points are sitting on top of it. Okay, so let's go to the Higgs boson itself, and let's look at the issue of mass. Now, mass, as I said, gives our universe substance. Now, to Newton, mass was F equals ma, which many of you are familiar with. And the weight of an object is mass times the gravitational constant in the field that you're in. And to Einstein, he had two things. For him, mass and energy were convertible currencies. But also, he said that mass actually has a fundamental property that it curves space-time. So in a sense, it is charge of gravity as such. Now, all of this is correct, but the question really arises, how do fundamental objects become massive? So how does the W and Z get a high mass and the photon remains massless when we unify electromagnetism and weak interaction? And that is what deep down the Brout-Englert mechanism is. And the simplest theory you can write down is that all fundamental particles are massless. If they're massless, then we can't describe the observed universe, because we wouldn't be here, because every particle would be traveling the speed of light. And so we will all be just puffs of radiation, so no structures could form. So it is rather fundamental to understand how that arises. So in the early 1960s, a bold intellectual conjecture was put forward that there's a field that pervades our entire universe, and particles interacting with this field, massless particles interacting with this field, will acquire mass. And the larger the mass, the stronger the interaction. And the field would be a quantum field, so the quantum of this field would be the Higgs boson, and finding the Higgs boson would establish the existence of this field. So that was what was actually the one way of a simplified way of looking at the Higgs boson. Now, boson in our detectors leaves very characteristic fingerprints, and the standard model has very well-defined couplings, the decay rates and the types of decays it might go into, and the angular distributions, as long as what it doesn't do is predict its mass. And so that's why it has been rather difficult to find, because the mass could have been anywhere, and we found it at 125 GeV. And it's a place where actually it can decay into many different ways. For example, it goes into BB bar, tau tau, ZZ, WW, to 2 photons, and so on, to dimuons, and so on. Now, it goes a lot of times to BB bar, but that has a very large background from quantum chromodynamic processes, which completely overwhelm the Higgs. So we never see it, essentially, although we've now figured out a way of actually seeing, getting signs of it. And that's where it, 55% of the time it goes into BB bar. But where we found it originally was in the gamma-gamma and the 4 lepton mode, ZZ, decaying to 4 leptons, could be electrons or muons. And here is 2 in 1,000, and here is 1 in 10,000. So we had to produce a very large number to have a few of these things appearing in our plots. And that's one of the reasons why it took so long actually to discover this thing. Not only its mass is very high, but the signatures it leaves, certainly in the hadron colliders, are not very clean. So this was pictures that we took right at the beginning. These are from 2012. So this is a Higgs boson being produced, decaying into 2 photons. So green, the height of the green bars there tells you the amount of energy that the photon was carrying. And if you take the energy in the direction of these 2 photons and combine them to effective mass, you can actually start plotting the effective mass of every time you see in a collision 2 photons. And in this case, there are 2 electrons shown in red here, and 2 muons shown by these bars here, which is a muon going through there. So what you do is you plot these things on the left-hand side top plot, the 2 photons and the 4 leptons. And most of the time, it's just random coincidences. You see nothing, it's just background. But in some places, it actually shows you a peak, and that tells you that you've found a particle. And that peak appears at the same mass in the 4 lepton channel as the 2 photon channel. So these are the gold-plated modes, if you wish. And the Atlas saw them at the same place as well. So that was the discovery in 2012. These are data which came much later, so you can see them more cleanly. But the most recent data actually allows to measure the couplings of the Higgs boson to the top quarks, the W's, the Z's, the bottoms, the taus, and the muons. And if it was a standard model Higgs, it would be sitting on a straight line, which it does. And the errors are at the level of 10%. But we also know that there are theories which are beyond the standard model, but they will only show deviations at the level of 1%. So we are still not at the level of less than 1% to be able to say that there is something else there. So that's why one of the reasons of actually asking for 10 times more data is to reduce these errors and see if there is any deviation. There could be deviations at a larger level than 1%. And by actually collecting a lot more data and improving our detectors, we then are probing the Higgs boson much more deeply, in a sense. So so that is what the mission is now going forward. So the known physics is measured as predicted. And so now we really concentrate on searches beyond the standard model. And there are three possibilities which I will develop, but there could be many others, some which we perhaps don't even know yet. Supersymmetry, extra dimensions, and the unexpected physics, which is was the last category I was just mentioning. Now, clearly, this is a thing that I showed you right at the beginning. Now, what I also wanted to convey to you is that the situation is quite concerning in a sense, in the way that it was concerning at the beginning of last century. And, you know, people at the beginning of last century felt that physics was all done and there was only details to be figured out. But then there were some niggling problems, like the black body radiation problem. And then the whole thing just developed from niggling problems. So we have several niggling problems, in fact, which we know. And there is experimental evidence that these are problems. For example, neutrinos have mass. And the Higgs boson has been found at 125 GeV, but it is also a particle that gets quantum corrections. All particles get quantum corrections. For example, the top quark gets it, and we have actually measured these things. But the problem here is that these quantum corrections float up the mass of the Higgs boson to the next scale up, and the next scale could be 10 to the 15 GeV. So you can see an object getting, with a mass of an order of 100 GeV, getting corrections at the level of 10 to the 15. It doesn't make sense. So there's something else happening. There's something protecting the mass, keeping the mass of the Higgs boson low. And what is it? It could be new physics. And supersymmetry actually fulfills that role. But we haven't found any evidence for it. We know there is matter-antimatter asymmetry, which we don't understand. We know there is dark on these rotational curves. We don't understand that. We don't know what it is. We know there is dark energy because the universe seems to be, expansion seems to be accelerating. So there's something pushing it out. And so what is it? And we have no idea. So these are really very, very big questions. And I guess the idea is to be able to try to find the answers to these questions. And so that is something which I'll touch upon, how to just proceed. So in a sense, the supersymmetry is quite an interesting theory. Whether it works and applies at the scale of the LHC is a question, but it's certainly there somewhere. It could be at the Planck scale. That's what Abdus Salam actually was talking about when I first joined the Imperial College group as a PhD student. He was his student was working on supersymmetry at the Planck scale. So there must be some relation between matter particles and force particles. It's too inelegant to keep them apart in a sense. So supersymmetry does that. And it predicts the existence of a partner for every known standard model particle with a spin differing by half a unit of h bar. And it also predicts 5 Higgs boson. One of them would be very, very similar to the Higgs boson we found, with couplings which are only a few percent different from the standard model, and that's where the 1% comes from. And the lightest particle of this species is a good candidate for dark matter. So in a sense, it's very elegant. It could solve many problems. But on the other hand, if you have a theory which tries to solve many problems, perhaps it's not the right one, because no such theory actually does everything. So maybe we're asking too much. Then you have the superstring theories, because one of the problems, how do you incorporate gravity into quantum theories of the other 3 interactions? And we don't know the answer to that. And the extra dimensions might help in understanding why gravity is weak compared to the other forces, much, much weaker. Maybe we live in, when we go to very small sizes, the number of dimensions that we live in is more than 4. And the gravity goes as 1 to the 1 over r to the power n minus 1, n being the number of dimensions. In the normal gravity that we're familiar with, 3 dimensions is 1 over r squared, which is a familiar inverse square law. So gravity could be very weak if it has a very high n, a large number of dimensions, for example. So let me now go to the next 20 years and then the following after the 2040. So the idea here is that in physics, certainly in LHC, the topmost priority in particle physics is the full exploitation of the LHC, so its full potential. And for that, we are actually starting to upgrade our detectors and the machine with a view to collecting about 10 times more data than the initial design. The initial design required us to collect 300 inverse femtobars. That's the unit of number of proton interactions that we have studied, and we want to increase that by a factor 10. The physics is that you would like, as I mentioned, to understand the Higgs boson very well. We would have produced about 150 million Higgs bosons rather than 15 that we would have done by this time. So it allows us to study in much finer detail some of the things that I was talking about, and also allows us to get a deeper search for physics beyond the standard model. We're not seeing anything, and the question arises, are we not seeing anything because there's nothing there, or are we not seeing it because we're not smart enough? And so one of the things is to increase the number of the statistics to probe areas which are probably not populated yet as much and see if there's something there. And also to make precision measurements. Sometimes you make a very precise measurement and it turns out that it's in contradiction with the prediction. And that gives you an indication of what's going on. Now, going further ahead, so the program of work that I was just mentioning, for which we are preparing, operating in about 2027, 2028, goes on to about 2040. So that's the point that I was making, where the Iranians are working on this link system for the Muon RPC system. So that will be part of the upgrade, and of course their contribution is highly welcome and appreciated, in fact. But there are many other parts of the detector which are being upgraded, and I'm personally working on one of them, which is the replacement of the NCAP calorimeters with something much more powerful, which will have a bigger physics reach. So the idea is not only to collect 10 times more data, but also to have detectors which are better than what they are today, to improve the type, to probe deeper the physics we're trying to do. So improve the quality of the detectors to get more physics out as such. Now, looking further ahead, one would like to increase the energy by a factor of 10, because every time we do that, something new crops up. Oftentimes it's unpredicted. And although nowadays things being very costly, you have to have some sort of a guarantee that something will be found. But in the old times, we just increased the energy and we always found something. Now, that doesn't need to continue forever, but the strategy was outlined in 2019, contains 2 points, an electron-positron Higgs factory in the highest priority next collider. So here, instead of 15 million, you are actually producing millions of Higgs bosons, but since it's an electron-positron machine, all Higgs bosons count. So there's no background as such. So every Higgs boson is, in a sense, gold-plated as such. So that allows you to study very rare processes, and also the precision with which you measure the couplings that I was talking to you about in a much finer way, and make contact with this 1% that I was talking to you about. Now, the other thing is Europe, together with its international partners, should investigate the technical and financial feasibility of a future hadron collider at CERN with the center mass energy of at least 100 TeV, with an electron-positive and electroweak factory as a possible first stage. So the idea here is the LHC sits around about like this. And that's the fountain in Geneva. That's the Geneva Lake. And that here, grayish, is the airport. And these are mountains. That's Mont Blanc there, right at the back. And these are local mountains called Salève, and this is taken from a mountain called Jura. The idea is if you want to get 100 TeV, you go underneath the lake at about 400 meters depth, go around this mountain and come back. And that's 100 kilometers. So it's obviously a very ambitious project. And so the current efforts are to see if CERN can actually get the resources to build such an accelerator. If you do build it, then it actually gives the scientific lifetime of such a thing is about 60, 70 years. Now remember, the LHC tunnel that we're using was started to be dug in the 70s, and we put the electron-positron machine and we took it out, and then we got the proton-proton machine, and the thing continues till about 2040. So that's about 70 years of work of science coming out of one tunnel that was dug in the 70s. So the idea is that can one do something similar? Of course, the upfront investment cost is very large, but it can be amortized over 60, 70, 80 years of science as such. So let me wrap up now. So now I've been talking about the standard model particle physics mostly on the left-hand side. On the right-hand side, you also have a standard model of cosmology. And that is a rather simplified version, in a sense, which says that 70% is dark energy, or around 25% is dark matter, and 5% is what I've been talking about. So we would like to know what these things are. And being particle physicists, we think they could be particulate in nature, but they could be something else. So there is some evidence that could be particulate in nature, in the sense that this is a plot on the left-hand side is a composite image, which is taken from various satellites. So it's called the bullet cluster, and the hot gas, which is shown in red, comes from the Chandra satellite, working in infrared, and that contains most of the normal matter, and you can see it is clumped together. So this is actually a collision of two galaxies, two clusters of galaxies, and they're actually going through each other. And the blue clumps are where most of the material is, because that you can figure out by gravitational lensing. And so most of the matter is sitting in these blue lumps and not in this reddish part. And so that suggests that the blue part has just gone right the way through and has not interacted. This stuff has interacted. And so this is probably interacting electromagnetically. And this either doesn't interact or it's a weak interaction. So it doesn't perturb the things too much. And that's a property of the lowest supersymmetric particle, lowest mass supersymmetric particle has that property. And so is this dark matter, which we can't see because it doesn't shine, and it's only deduced by gravitational lensing, by gravitational means, and so it is obviously interacting gravitationally. Is the lighter supersymmetric particle responsible for this? But we have not seen any evidence for that. We were hoping that one of the first things we would find is this, but it didn't happen. On the right-hand side is effect of dark energy. So there are two ways of actually figuring out that there is dark energy, which is 70% of the energy matter density in the universe. One is through the supernovae, where it tells you that the expansion of the universe is accelerating. The other one is to take the cosmic microwave background radiation maps and trying to understand the structure of that. And that tells you how much dark matter, dark energy, and normal matter. You can figure it out, and it comes out to be the same amount, essentially. One of the things about the acceleration of the expansion of the universe is that if you take a bath of Higgs bosons, they exert negative pressure. They seem to have a property which would be necessary to actually explain the acceleration of the expansion of the universe. So meaning something is pushing things out. Gravity only pulls things inwards. It doesn't push outwards. So there has to be something like that. So the question has arisen, and it's one conjecture of many, is dark energy responsible, is a remnant of some elementary scalar field analogous to the bright angular Higgs field? So that's an open question. So you can see that in trying to understand these questions, we fold back into particle physics. So the relation between particle physics and cosmology is quite strong in a sense. So let me come to the last point, which I said I would say a few words. Now, this is the history of the universe. So I'm trying to bring everything that I've said together in this slide and see and then try to make sense of our understanding of the universe as such. Now, it is conjectured that the universe came into being in a cataclysmic event, the hot Big Bang. So this is here. And the universe has been expanding ever since, and this expansion line is indicating the expansion of the universe. And when it expands, obviously, it cools down. So from the earliest moments of the Big Bang, when the temperature was 10 to the 32, which is shown here, degrees, and the equivalent time and the equivalent energy is shown here. This is the Planck energy, 10 to the 19 GeV. The gravitational force soon became distinct in its action with respect to the other three fundamental forces, strong, electromagnetic, and weak. So in a sense, we say gravity froze out. And then from various astronomical measurements, we know that the universe is flat. What does it mean, flat? It looks the same in all directions with the same cosmic microwave background temperature after the gross distortions due to our own galaxy are factored out at the level of 1 part in 10 to the 5. Now, what I showed you in the map before was lower than 1 part in 10 to the 5. And there's also evidence of the observed abundance of helium and other light elements like helium and helium and lithium are too great to be synthesized in stars. So there was some nuclear synthesis was taking place in the early part of the universe, because the galaxies only came at about a billion years in this epoch here. This epoch here. And so we have too much helium and other light elements to be, so something was happening there. Now, so the first two conditions are conjectured to be due to an epoch, which is called inflation. So there was a rapid expansion of the universe, which makes it look like, looks the same in every direction you look at. And also, and so in this period, the size of the universe increased exponentially. This was happening at 10 to the minus 37th of a second for about a brief moment, from 10 to the minus 37 to 10 to the minus 35. So it's a brief moment, but expanded exponentially. And so when the inflationary period stopped abruptly around 10 to the minus 35 seconds, much of the energy of the universe was used up in creating particles of the standard model of particle physics, such as the quarks, gluons, Ws, and Zs. And you can see this thing here: the photons, quarks, gluons, neutrinos, and electrons, and so on. Now, we should also add Higgs bosons in there because we know that they exist. So as the temperature of the universe dropped, the strong force actually froze out, and the matter and antimatter asymmetry arose. So that's the moment where we think the antimatter asymmetry took place here. Now, the proton-proton collisions of the LHC through the head-on collisions of the quarks and gluons inside the proton, probing the physics at an instance around about a picosecond, so 10 to the minus 10 seconds. So this is what the LHC is doing. So you can see an arrow of the LHC, and Tevatron was there, and Rick is here. So you can see we're actually tracing. So we're probing the particles that existed in this area here, and now we know that the Higgs boson also. So in a sense, we are able to create whatever particles existed in this era, and the hope was that we would also find some supersymmetric particles being present in our universe. And of course, we haven't found them, but maybe they were at an earlier moment, at a higher energy and a higher mass, or something of that nature. At this point, the temperature, which is equivalent to about 100 GeV, this is where the electroweak phase transition took place, where the electromagnetism and the weak forces became distinct in their action. And this is a quite interesting epoch that we would need to study. So if you went to a 100 TeV collider, we would be able to work out what the Higgs potential looks like. And that is the potential that is actually relevant for the determining what type of phase transition took place. So it's like trying to do electromagnetism without knowing the Coulomb potential. If you know the Coulomb potential, you are very powerful in predicting many of the things. So the situation is rather similar. So we'd like to know the form of the Higgs potential, And that we will know if we go to an accelerator about 100 TeV. And that could tell us exactly what was happening and how matter-antimatter asymmetry arose, and answer some of the fundamental questions. Now, clearly, as the temperature decreased further, as you can see, 10 to the 15, 10 to the 12, 10 to the 9, 3,000 degrees Kelvin, the quarks and the gluons coalescing. So this is this area here, into protons and neutrons. And so a phase transition is said to have taken place. We had a quark-gluon fluid before, and then it started coalescing into objects. So this transition is thought to have taken place around a microsecond, or around by that time. And this is exactly the sort of things that the lead-iron collisions in the LHC actually are creating. So we're creating conditions where the neutrons and protons in lead nuclei melt into a fluid, which was present in our universe about a microsecond after the Big Bang. So we can study those kind of phase transitions as such. Now, as the universe cooled further, and you started making atoms as such, and as the universe cooled even further, then the photons did not have enough energy to break up, let's say, a hydrogen atom. And so the photons became transparent in a sense, and that's where the cosmic microwave background radiation that originates from. And that the decrease of energy is cooling down also the stretching of space, because I think I shouldn't forget that the space is being stretched, and that means the wavelength of the photons is being stretched and going to longer and longer wavelengths. And today, what we measure as relics from this epoch have a temperature of 2.7 degrees, which is the cosmic microwave background radiation. So when I showed you a map, we're actually looking at a map of the universe at this time. Now, later on, about 1 billion years later, places which had a high mass energy density would then seed galaxies. And for that, having dark matter, if you run relations without dark matter, it's very difficult to form galaxies. And so people have actually the dark matter is required to form galaxies, and galaxies are needed to be formed for us to exist, and to be able to observe what has been happening. So that gives you an idea of the history of the universe, and in terms of also particle physics. And so a lot of the things that we think we know actually come from the work that has been done at the accelerators and over the last 50 years. So let me summarize. So over the last 50 years, the creation of the standard model of particle physics, it does represent a towering intellectual achievement of humankind, both experimental and theoretical. And so this has allowed us to trace in much more detail the evolution of our universe from early moments after the Big Bang, which is what I've just said. Now, at the LHC, we have discovered this keystone of the model, the Higgs boson. It appears to be the one that is predicted by the standard model. Now, we're trying to study that in great detail. We haven't found any evidence of widely anticipated new physics. And I think we were all quite anxious to see that in the early 90s. It hasn't turned out. So, as I said, we have to look harder. But the other thing that I also wanted to pass on to you, that we're just at the start of this exploration, because we've taken about 150 inverse femtobars and we want to go to 3,000. So even in the original 300, we're only halfway. So there's a lot ahead of us, and the question really arises: what further discoveries await us? And I gave you some impression of the fact that several of the open questions today are just as profound as those that were a century ago. And there are many places to look for this new physics, obviously, in LHC is the only one, but it's perhaps the foremost place to look for new physics. And one thing I also wanted to communicate is that when we make discoveries in fundamental science, they invariably lead to paradigm-shifting technologies. And I just gave an example of the discovery of the Dirac's equation, which is a very esoteric mathematical entity in a sense, but it had quite profound implications in terms of technologies and the GPS technologies from work of Einstein as such. And so almost everywhere you look, and you can't live without electronics any longer. Wherever you look, you'll find fundamental science at the heart of it. And the last point is also, in a sense, it's an obvious thing. If we stop doing experiments, we will stop gaining knowledge and we'll move into metaphysics. So only experiments reveal or confirm nature's secrets. So we must continue doing experiments, even if they end up costing a bit. But that's where collaborative science of the type we're doing comes in, where we share the intellectual and financial capital of the world to come together and do some things together. Let me stop there. Thank you. I'll switch my camera on.
Well, thank you very much, Jim, for beautiful talk. Very informative. And now we are open to questions. Any questions? Well, I ask Amin to administrate the questions.
Yes, thank you very much for the beautiful talk. Yes, please raise your hand. I will change the role to presenter. Then you would be able to turn on your microphone and camera, and you can ask the question. You can also type the question in the chat box, and I can read it for you. Okay. Selma Rezavand, please go ahead.
Can you see, am I upside down or?
No, we see you from the side.
Okay, so let me just move the thing to the center. Because my computer doesn't seem to work, so I have to use my iPad.
Okay, now we see you.
Yeah. So what is this thing here? Is a pen. Okay, so who's going to ask? I wonder if particle experiment.
Yes.
So the way that the particle antimatter experiments are done is to particle, for example, and its antiparticle can decay into the same final state, and you tag it, and if there's a difference between the particle and the antiparticle in the decay rates, that tells you that you have violated a symmetry, and that is one of the clues, because the particle matter antimatter symmetry requires in fact three things to actually to understand it. One is that there's a symmetry called charge conjugation and parity. Charge conjugation means that you change the charge of the particle. For example, an electron becomes a positron. And then parity means that you observe the experiment in a mirror, and that should not actually affect your results, but it turned out that it does in some weak interaction processes. So you need the CP symmetry to be violated. These are called the Sakharov conditions, which were set forth by Andrei Sakharov in the mid-60s. The other one is that the universe, what's called the baryon number, which is the, for example, the proton has a baryon number 1, an antiproton would have a -1, and that number has to be violated. So the number of baryons has to change. And the third thing is that the process of the decay that I just mentioned has to take place when the universe is not in thermal equilibrium. So the temperature is changing during, and so those three conditions have to be satisfied. Now, what we observe, we have observed CP violation in K systems and B systems. The K1 is an object made out of a U quark and a strange quark, and the B systems are made out of B quarks, either U or S. And so we actually see this violation taking place. the amount is not sufficient to actually account for the baryon the matter symmetry that we observe in the universe.
Okay, Selma.
So there was how seismic noise affects certain data. As I mentioned, the is because what we're looking at effects. Gravity doesn't affect things very much at all, and so these things affect things like gravitational wave detection because it's very precise, very fine and sensitive. But the work that we do actually requires strength of the interaction, like the electromagnetic interaction, is relatively strong. Although it's not as strong as the interaction that binds quarks together in protons and neutrons. Now, if there was even a small imbalance between the charge of the proton, for example, as far as the hydrogen is concerned, you wouldn't be able to form it. So seismic. We have to worry about seismic. As far as the stability of mechanical stability. Design them so they don't actually fall apart when there's an earthquake. So that we have to take into account. So it's more for the physical safety of the instruments rather than the sensitivity.
Hello, can you hear me? Can you hear me, sir?
Did you hear?
Yes.
Okay, I'm Selma Rezavand, and I have a question about Big Bang. Given that the universe has been expanding for billions of years, and it may have gone through a contraction phase before the Big Bang. Although I know asking about before time started is not proper, but is it correct? And if so, will the universe expand forever or will collapse?
Yeah, I think you're asking a question about the origin of the Big Bang, and of course, we don't have the theories that tell us the answer to that question. A point that has been made, meaning that the universe is cyclic in nature, so it just expands and contracts and expands and contracts, and then the origin of time becomes mute because it's been doing it for an infinite amount of time. So it's not 13.7 billion years, as we say, but it's infinitely. One way out of saying that I don't have to worry about the origin because it's cyclic. Another way of looking at it is that we're living in one universe and there are billions and billions and billions of other universes, multiverses, if you wish. And so what we observe in our universe is only appropriate to our universe, and things are the way they are. And so in that sense, this is a bit of a defeatist way of thinking, because the idea of getting a unified theory is that we would be able to work out everything about a universe from first principles. For example, even though the standard model is very successful, many of the things like how what the charge of the electron is, what the mass of the electron is, and mass of the quarks, and all sorts of things are put in by hand. We measure them and we put them in. And so that's not terribly satisfactory because it's not principles. So the idea is that if you get to your unified theory, you'd be able to get those values out automatically. Now, another stream of thought is that in another universe, these values would be different. Could be different. Since there are an infinite number of universes, you can have an infinite set of values. But life in those universes will be different from ones that we have. Now, again, these are conjectures. And part of the thing that I mentioned right at the end is that if you can't test something by an experiment, the conjectures are just as equally valid as any other conjecture. So you can't tell. And that's part of the problem of conjectures. So you have to have an experiment that actually says this is what nature is telling you. and that's the nature's choice. And then we don't have any freedom. We can't contradict nature's choice. In other words, it is what it is, and we have to what nature is chosen to do. We can't put our own impression on it.
Thank you, sir.
And there are some questions in chat box. Can you?
We're starting to install the. I've missed a question.
I can read it for you if you like. But
yeah, instead of smashing particles to reach high energy, looking into the center of galaxies and other high energy sources and where energy is supposed to be high. Yes, I think as I was trying to indicate, there are many ways of trying to get information about the questions that we're trying to answer. And certainly astrophysics looking into those kind of phenomena is in learn a lot. For example, the gravitational waves have been discovered by looking at merging of black holes and so on. Now, the problem usually is that these are not controlled ways of doing things. They happen, and if you're lucky, you pick them up. So whereas in particle physics, what we try to do is to create beams which we then control and make them interact, and so in a very controlled way. So we're actually repeating the experiment. And for example, to give you an idea, the number of Higgs bosons being produced in the outer atmosphere, even now, is larger than what we produce at CERN every second. But the problem is we don't have a detector which covers the whole surface of the Earth. If you had, then we wouldn't need an accelerator, but we can't do that. So that's another way of looking at it. These interactions are taking place in the universe, and they're taking place in the atmosphere, and people study them. So you look, and we try to understand the origin of these particles coming from outer space as such. So there are different types of experiments that allow you to actually probe different things, but they're all needed, and results from all of them are combined together. And in a sense, what I've actually said is I brought in some of the astronomical observations and other types of observations to build a picture of what's happening in our universe as such. So it is true that we need to be doing different types of experiments, and not only the ones that I've talked about. And there's another one. Let's see. Next question is point of view about gravitational waves popped up nowadays, which I heard is not relative to the first 100 years of universe. I didn't quite understand that question. Maybe Hesam, would you be able to understand that question?
I think she is asking about the relation between possible relation between gravitational waves and particle physics experiments.
Yeah, I think obviously in the science is quite different, but in a sense the aspect of fundamental physics is similar. Is a way of actually understanding gravity. We've been in accelerator physics and particle physics, we tend to look at the three other interactions. So that's the first notion that, gravitational waves, there's a particle involved, which is a graviton and so on. And so in that sense, it is fundamental. It took us a long time to get there, to find the first gravitational waves, because the sensitivity had to be very, very high, and took technology time to catch up to such sensitivities. But there's no particular direct relation between particle physics and gravitational waves. They may well turn out to be technological connection, because the new observatories people are talking about, like the Einstein telescope, which will be a triangle of side of equilateral triangle of side of 10 kilometers, will require technologies which we use in particle physics, like high vacuum tunneling, high stability of instruments, and so on and so on. So there could be a technological connection, but in terms of the fundamental physics, it's somewhat different, because we don't take account of gravitational effects, terribly minor.
Okay, thanks. Any other question? Raise your hand or just type your question in the chat box.
And there is a question about gem detectors. Are the gem detection system at CMS setup? What is the role of them exactly?
Sorry, could you repeat that, please?
Well, there is a question that says, are there gem detections systems?
Oh, yes.
Yeah, what is the role?
So, yeah, in fact, we developed the, so this is where the evolution of technology comes in. Gem detectors were not available about 20, 30 years ago. And so they operate in, they can operate with high fluxes compared to the current detectors in our muon system. So these are gas chambers, and they allow the measurement of the passage of particles to higher precision, allow a higher rate of particles passing through, and keep them separate. And so we're installing them in the areas where, in the end cap areas. In fact, the area that as a supplementary detector to the RPCs that I mentioned that the Iranians are working on. So it's to have a second detector with similar capabilities, slightly different capabilities, to enable us to increase the amount of physics we can do. So they have gone in, a few detectors have already been installed, and they're working well. And they're being actually made by Indians, Pakistanis, and groups in Italy and Europe. So that's one way of actually transferring technical know-how to countries which are new to particle physics, because there are for countries like the countries that have a newer tradition in particle physics, they can actually do these kind of things, whereas some of the detectors, like pixel detectors, require a lot of knowledge beforehand, expertise, and that takes a bit of time to acquire.
Mm-hmm. There's another question.
Farhad said that you mentioned that a theory, if a theory explains it. Oh, well, what I meant there, sorry, I actually perhaps misspoke. You know, when I was growing up, or cutting my academic teeth, supersymmetry was invoked to sort out the problem of proton decay, because the proton decay was not occurring at the rate standard model or some extensions the standard model would have predicted. It also had this nice feature of explaining dark matter. It had a nice feature of explaining why the Higgs boson would have a mass low mass, and so on. So in a sense, what I was saying is that, you know, we're asking a lot of a theory, and we don't even know whether the theory is relevant at our energy scale. And so in that sense, perhaps asking a theory to explain everything we don't understand perhaps is asking too much. It may well turn out to be true. It could turn out to be true, but it's more a word of caution. And there was nothing profound in it.
Okay. Any other?
This is your question, Farhad.
Yes.
Okay.
If there is not any other question, I think Reza Mansouri, you have the closing remarks.
Okay.
Reza?
Okay, yes. I'm so sorry that I was interrupted. some technological defect in my laptop. But I'm really very pleased to see that you are lecturing, you're talking here for us in Iran, and hope to see you again at CERN or in Iran again, and hope very much.
Iran.
Yes, why not? And let's hope that the next accelerator at CERN in 15 or 6 years, I will be ready there to see that again.
Yes.
And you too, surely.
We'll try.
Thank you very much. Thank you very much.
Try our best.
Yes.
Good to hear from you, Reza.
Yes. Jim, I think that somehow our publics in Iran could realize how complicated not only the technology and science behind LHC was, but also the management. You see? That was something that I've been always, I was always strange. How do you manage it with a couple of hundred institutions, more than 3 or some 4,000 people, scientists, engineers, all working together to see the boson Higgs, you see? So the management must be much too difficult for us, at least for us in Iran, to understand how you manage it, you see?
Yeah, I think there's also a question of the language. I think the language we use is the language of science, and that is universal. It is not, and it's the culture of science is also universal. I think Abdus Salam actually mentioned that the culture of science is universal and has always been universal. And so the other thing that I think helps a lot is that the egos can be controlled, because what we're trying to do is to find out what nature is about. And if you make a mistake, or if you cut corners, or if you have an ego, nature doesn't care about that. It will punish you if you make a mistake. And so you better get things right. And so I think every institution, even and including yours, they try to do their best to make sure that they are not responsible for any possible shortcoming in the experiment. And I think everybody works from that point of view. So they try to do their best. And the other thing that I think is quite important is, if you are in trouble, people do speak up in the experiments, and they don't keep quiet, because somebody can come and help you. And because you're actually, by have a problem, you're helping the experiment. So I think there are various reasons why, experiments like CMS with so many people can work, because the criteria that we use are not the normal criteria, where egos and profits and all sorts of things like that come into play. So it's a different, I think, environment, and it should be replicated in many other areas of our social discourse. It would be good. We would not have as much strife.
Exactly. Let's hope that from CERN, from LHC, and from CMS. Thank you very much, Jim. Thank you.
Okay, thank you.
Thank you very much, Jim, for a wonderful talk. But before closing the session, let me announce one point. Well, our next lecture in this series will be on 16th of September, and David Gross will talk to us. Which is actually on the Iranian calendar. It is 25th of Shahrivar. It's a Thursday. Just I'm announcing it, and hope to see you there too. If you are interested, I will send you the information. Thank you very much, Jim. It was wonderful talk.
Bye-bye, Sam, and good luck to you all.
Thank you. Bye.
Bye-bye. Bye-bye, everybody.